All right, folks, it's Bass Action back in action here. In this video, we are going to look at symmetry related to graphs, and we are going to look at this symmetry both graphically and algebraically. We're going to use these concepts throughout the entire year, so we want to understand these well from a variety of perspectives. We're going to start off here at the top looking at things graphically. Now this is going to start off pretty simple. I've got 3 different images here, and we're going to look at their types of symmetry. Now you'll notice that in the video here, I've got 2 different colors for the graphs. On your handout, they might look the same. So you might want to pause the video and color them so that they match mine, so that you can see that we've got a graph here, and this is our graph that we're starting with each time, and then we're going to indicate the various symmetries. So if our graph started off looking like this top one here, we can see that this graph is symmetric. The blue graph is now symmetric with respect to the x-axis. Moving on, you can see that we've got one here. This graph then, the pink one, is symmetric with respect to the y-axis to the blue one. And then over here, we've got a pink and a blue, and these are symmetric with respect to what we would call rotational symmetry around origin. Now, what's going to actually happen for us is that we might be given this pink graph, and we need to find points that have the appropriate symmetry. So, for example, let's say we have a point right here, -3, 7, and we want to find a point that has symmetry with respect to the x-axis to this point right here. What we would want to do in that case is we would want to visualize our point -3, 7 would be in this second quadrant, and if it was going to have symmetry with respect to the x-axis, it would appear down here in the third quadrant. Now up here you can see what the rule that's actually happening. We can see that the x-coordinate is going to stay the same, but the y-coordinate is going to change sign. So if we want to know where is this point in the third quadrant, we are going to keep that x-coordinate the same, and the y-coordinate is going to change sign. If we wanted to find the point over here, following the same idea, now we want symmetry with respect to the y-axis. Again, we could put that point in its proper quadrant. It would be in the second quadrant. Now we want symmetry with respect to the y-axis, so that point would need to appear over here in the first quadrant. Looking at our points up here, these 2 comparisons, we can see that the x-coordinate is what is changing sign this time, but the y-coordinate is staying the same. Now that's what we'll do for this ordered pair. The x-coordinate now is going to change sign to the positive sign, and the y-coordinate is going to stay the same. Drawing this little picture is going to help you figure these out instead of having to memorize a bunch of rules. Over here, with symmetry with respect to origin, this is called rotational symmetry. Again, I'm going to put the point in the second quadrant where it's supposed to be, and its symmetry, if we're going to have the symmetry around origin, is now going to appear down here in the fourth quadrant. Looking at the rules that I have going on up here, now we can see that both the x and the y coordinates are going to change sign. So using our point, the x coordinate is going to become positive, the y coordinate is going to change. So sometimes we will ask you to literally just tell us where is the point with the appropriate symmetry. What we're going to do, though, with these rules is we're going to continue applying this to finding some other algebraic tests. So what we will eventually do is we are going to test equations for appropriate types of symmetry, and we're going to test functions for certain types of symmetry. Now, if we want to test an equation for a certain type of symmetry, what we could do, let's say we want to test an equation. Now, this word equation is important versus a function. If we want to test an equation for this x-axis symmetry, we're going to use this idea here, this rule that we did here, to understand this right here. What we will do is we will let y equal -y in the equation, and then we'll compare the result to the original equation. If the two match after we do the substitution, then we would say that it has x-axis symmetry. For our y-axis symmetry, again, we're really following this same idea right here. We're going to let x equal negative x in the equation, and again, we'll compare the result to the original equation. If the original equation and what we get after we do the substitution is the same, then we would say that the equation has y-axis symmetry. Lastly, if we want to test symmetry with respect to origin, now we're going to do both. Just like we did both up here, we're going to do both on our equation. We're going to let x equal negative x, and we're going to let y equal negative y, and then compare the result to the original equation. If in any case, when we do the substitution and we compare to the original, if they don't match, then the symmetry does not exist. Now, what we're going to do is we're going to extend this idea of testing equations, and we're going to narrow it down to just functions. What we want to remember is that not all equations are functions. In order for something to be a function, it has to pass a vertical line test. Because of that, no function is going to have x-axis symmetry. And so then there is no test. So let's give that as our summary. So we're going to have no x-axis symmetry. I'm going to do some abbreviating here. No axis symmetry for a function. I'm going to abbreviate the word function for FCTN because it would fail the vertical line test that we did for our functions. So for example, if I had a graph that looked like this left-right parabola that we will eventually study, this left-right parabola, this graph would fail the vertical line test, so it couldn't have any x-axis symmetry. Okay, now let's take a look at these two. These are the two that we're going to really spend our time on. Our y-axis symmetry test for a function. Again, it is related to what we're going to do here. What we're going to do on these problems, since we can work with our function notation, I'm going to slide this up a little, since we can work with function notation, is we are going to compare f of x, the original function, we're going to compare that to f of negative x. Notice that f of negative x, this is just like letting x equal negative x, which is what we did up here. If those two are the same, then we will say that the function is even. Now, I want to emphasize that a function being even is not related to the degree of the function. This is a specific type of symmetry behavior. For origin symmetry, what we're going to compare is f of negative x, and we're going to compare that to negative f of x. This also is the same as what we did up here. This negative x is our x equal negative x, and this negative f of x is the same as our y as our negative y. If these two turn out to be the same, then the function will be said to be odd. Now, these are specific titles. They are not related to the degree of the function necessarily. So let's take a look at how this is going to work. We are going to test this algebraically. Now, you might know what these graphs look like. You could even go and graph them in Desmos and verify that these tests are true. So what we will do each time, we've got our original function, and then we're going to find the two things that were mentioned up here, f of negative x and negative f of x. So we're going to find those and do some comparing. All right, let's find f of negative x. F of negative x says we're going to let x equal negative x. We want to be careful with our parentheses here. And if we simplify this, negative x times negative x, because we're going to square it, this is going to become 5x squared minus 7. If we wanted to find negative f of x, what that is asking us to do is to distribute the negative to the entire function. So if we distribute the negative, we would get negative 5x squared plus 7. Now, when we compare the original, the f of negative x, and the negative f of x, what we can see is that f of x and our f of negative x, those are the ones that are equal. Since f of x equals f of negative x, this function is even. Next, let's take a look at this rational function. I'm going to tell you right now, these are tricky for students because they want to do funny things with our negatives. Let's find, slide this up again, let's find f of negative x. Again, that means everywhere we see x, we're going to put negative x. So negative x squared minus 4, and in the denominator, I have 2 times negative x. This is going to clean up to be x squared minus 4 and a negative 2x in the denominator. This could also be rewritten. I could take this negative from the denominator and move it to the top, but then I would have to distribute it. So this is also the same as negative x squared plus 4 over a 2x. Now, we're also going to find our negative f of x. That means that we are going to put that negative, we are either going to put the negative and distribute to the numerator or distribute to the denominator, but not both, okay? So let's say we want to distribute it to the numerator. That would give us negative x squared plus 4 over 2x, or I could put that negative in the denominator, leaving the numerator alone, and I could put it in the denominator. Again, it either gets distributed to the numerator or it goes to the denominator, but don't do both. Now let's compare. F of x and f of negative x, these are not equal. If we look at these numerators, these are not the same. But if we look at our f of negative x and our negative f of x, we can see that these are the same. These are now the same. We got the same value each time. That means that f of negative x equals negative f of x, so this function would be odd. Now, I'm going to pause here to remind you, if you, after this video is done, if you enter this equation into Desmos, you will find that because it is even, because we algebraically found that it's even, it should have y-axis symmetry when you go graph it. This one we can even visualize. It's a parabola that's been shifted down. It has a vertical stretch, but it's just been shifted. This function, you wouldn't know what this one looks like right now, but if you take this one and enter it into Desmos, because we found algebraically it's odd, you are also going to see that it has symmetry around origin, meaning either on the first and third quadrants will look like they are a rotational symmetry, or the second and the fourth. The last one we're going to look at, I want you to notice that this is not a function, this is just an equation, okay? Now we actually know what this graphs, okay? We should recognize this one. I'm going to get to what it graphs in a second, but for right now, I'm going to go ahead and I'm going to do our testing. If we do our equation testing for this, and I first test for x-axis symmetry, what we will find is we are going to let our y equal negative y in the equation. So we would have x minus 5 and then when I clean that up, that's going to get me an x minus 5 squared plus y squared equals 15. We can see that these are the same, so this equation should have x-axis symmetry. If we want to, oops, I don't know what that just did. If we want to test for our y-axis symmetry, In this case, we're going to let x equal negative x. So now if we put a negative x into our function, we can immediately see that this is not the same as this. So it is not going to have x-axis symmetry. Our last one we could check is we could also check the symmetry around origin, in which case we would change both. We would have our negative x minus 5. And we already know from before that if we substitute in our negative y here, this will become y squared. So again, these are not the same. We're comparing to the original. This one also fails, so it does not have that. Now, as a quick reminder, let's think about what this looks like if we graph this. So if we graph this, this is going to be a circle with the center at 5, 0, and a radius of the square root of 15. So it's going to be something just a little bit less than 4. And that would be our circle, and it would actually check out. So make sure that you've got this down. I would really, really encourage you to also go check those two equations in Desmo so you can see the visual aspect of the symmetry in addition to the algebraic test.